Swayam Prabha. Digital India. Educated India.
Continue from where we left last time. So we have now switched to basically correcting the ideal gas equation. So so last time we saw that in a real gas, two postulates they break down. One is that the size of molecules is zero, like molecules are dimensionless. That is not true for real gases. And the other postulate was that intermolecular interaction or especially attraction was negligible in ideal gases, it's zero, but that is also not the case for real gases, right? And in the last class we derived what's known as real gas equation, or also van der Waals equation of state. So real gas equation, which is also known as van der Waals equation of state, right? And we saw for n moles of gas, so this looks as follows: P plus A n squared by V squared times B minus NB equals nRT, right? And this was actually motivated from the experiments done by Andrew, like Andrew's experiments which were done on carbon dioxide. So what he did was, so he varied the pressure and volume of carbon dioxide gases and plotted the isotherms for various temperatures, right? And interestingly, he saw that so if this is pressure and this is volume, so at very high temperatures, so P always decreased as inverse of V, but so at certain temperature, I can quickly check. So this was like at 48 degrees Celsius, but as he decreased the temperature, there was significant deviation from the Boyle's law, right? So he observed significant deviation from the Boyle's law. Okay, and so much so that at certain point this curve almost became flat, and at even lower temperature there was a saturation before it decayed, right? And for example, this was 32.5 degrees Celsius. The next temperature was 31 degrees Celsius, which was the critical temperature, and at even lower temperature like 21 degrees Celsius there was a plateau, and based upon that he basically and he also observed that inside this region there was phase transition. So this is condensation. Here the carbon dioxide remained in gas phase, and here the carbon dioxide was completely liquid. Okay, so these were the experimental observations, but the important point is that the P scaling with inverse V, that started breaking down as the temperature of the gas was lowered. All right, and we imagined that this is only possible, and basically we saw that this could the gas can liquefy only if there are attractive forces acting between the molecules, right? And towards the end of the class, so when we derived this, so we wrote down the form of pressure from this equation for 1 mole of gas, which looked like RT divided by V minus P minus A divided by V squared, right? And we basically plotted this relationship of pressure as a function of volume, similar to Andrew's experiment, right? And we saw that so when when the temperature of the gas is very high, we can always ignore the interatomic, intermolecular attractions, right? In which case the system will, the only first term will dominate, so it will be like inverse 1 by V minus B, right? So if I can plot this as B, so at very high temperatures, typical 1 by V minus B scaling will be true. But as we keep on decreasing the temperature, the contribution from this term becomes more and more important, and we start seeing deviations in the functional form, right? Something like that. And so much so that after certain point, this function has a well-defined minimum. All right. Maybe I can draw it a little bit better. So this function start displaying a well-defined minimum, right? So this is Andrews experiment, and this is van der Waals equation, right? So I'll come back to this. I will basically after some time we'll basically compare these two plots again, and we'll see how they mean the same thing. All right. Another important thing that I also mentioned in the last class was about this critical point x, right? So in Andrews experiment, we observed that this critical point x is defined by three parameters. One is the critical pressure, other is critical volume, and other is critical temperature, right? And this critical point is the point beyond which we can see the phase transition, right? So for example, the critical pressure is defined as the pressure above which the gas can never be liquefied, the critical temperature is the temperature which in case of carbon dioxide is 31 degrees Celsius, right? For certain volume, no matter how much pressure we apply, if our temperature is greater than critical temperature, the gas can never liquefy. All right. So let us see whether we can calculate the critical pressure, temperature, and volume from the van der Waals equation. So remember, even in this case, there will be a point where this curve will become flat, right? And this will be the corresponding critical point from the van der Waals equation of state. Okay. So let us evaluate the critical parameters, right? So critical parameters from real gas equation. All right. So like I said, the critical point corresponds to the value where the pressure does not depend on volume anymore, right? So at the critical point, so basically dP by dV becomes 0, right? So pressure is not function of volume anymore, right? And what we will do is we will just substitute the pressure from here into that equation, right? So this implies we can write d by dV of RT divided by V minus B minus A by V squared, and that we will basically just equate it to 0, right? And if we do this little bit of algebra, so here you can see we get minus RT divided by V minus B whole squared minus, which becomes plus 2A by V cubed, that is equal to 0. And from here, if you do little bit of reshuffling, we can see that the temperature becomes 2A times V minus B whole squared divided by RV cube. All right. So let us call this equation 2. Let us call this equation 1, which is the real gas equation. All right. So what we'll do is we'll now substitute this temperature in equation 1, right? So substituting T in, or basically substituting equation 2 in equation 1, right? So we'll just substitute this T here, right? So we can see that the pressure becomes R divided by V minus B times 2A times V minus B squared divided by RV cube minus A divided by V squared, right? And this can be just, okay, so I'm just simplifying this term a little bit. So this becomes 2A times, so V minus B cancels out, so 1V minus B remains, divided by V cube, so R also cancels out, right? Minus A by V squared, and again, so this can be written as A times V minus 2B divided by V cube. Alright, and let us call this equation number 3. Okay, and this is the pressure, right? And now we can again use the condition that at the critical point the derivative of pressure with respect to volume is 0, right? So again, at the critical point dP by dV is 0, and all we have to do is we just have to take derivative of equation 3 with respect to P, with respect to V, right? So that will, so you can quickly check that we get something like 3A divided by V raised to the power 4 times V minus 2B plus A divided by V cube, right? So basically I've just done, first I have differentiated this term and then differentiated the other term, and this will be 0, right? And then this happens, and okay, and this gives us the value of volume. So if you do little bit of algebra, you can convince yourself that Vc in this case is nothing but equal to 3B, where Vc is the critical volume. Okay, so at the critical point we know what is the value of critical volume. So now what we can do is we can substitute the value of critical volume into equation number 2 and calculate the critical temperature, right? So substituting Vc in 2, right? And you can readily check that your critical temperature, so I'm just substituting here, the critical temperature becomes 2A times 2B squared divided by 27B cube R, right? So all I have done is I have just substituted for V here, okay, Vc here, and we get Tc, okay. And if you simplify this a little bit, so this basically becomes 8A divided by 27 times BR, okay, and this is our critical temperature, okay. This is the value of critical temperature, and similarly now we can use equation number 3, right, to calculate critical pressure, right? So now we can substitute Vc here, okay. So substituting Vc in equation 3, right? So if we plug Vc equals 3B here, so we simply get, so Vc A times 3B minus 2B divided by 27B cube, and this simply becomes this implies our PC is A divided by 27 B squared. Okay. So from real gas equation, we have calculated the values of temperature, pressure, and volume at the critical point. Okay. And now we can okay. And remember, in the last class I showed for various gases. Okay, maybe I can do that again. So experiments. Okay, so maybe on the next page. So experimentally, it was observed for various gases. There were various values of critical temperature, critical pressure. This is in atmosphere, and critical volume. This is in centimeter cube. Okay. So for example, for helium, hydrogen, oxygen, carbon dioxide, right? So we saw this is minus 268, 2.25, 15.4, minus 240, 12.8, 32.2, minus 119, 49.7, 2.32, and 31, 72.8, 2.17. Okay, so these are experimentally measured quantities, and more interestingly, now we can calculate the ratio of RTC divided by PCVC, right? And the reason we are doing this is because from ideal gas equation we know that PV equals RT. So for any pressure, volume, or temperature, PV by RT should be equal to 1, right? Or RT by PV, which implies RT divided by PV should always be equal to 1, no matter what are the values of pressure, temperature, or volume, right? But now experimentally we can now calculate these values. If we just plug this here, now you have to convert this into Kelvin, right? And they saw that these numbers take this form. So 3.13, 3.28, and 3.42 and 3.48. Okay. So even though the critical values for different gases vary drastically, right, from gas to gas, the ratio of RTC and PCVC was always lies between 3 and 3.5, right, 3.5. Okay. But now what we can do is we can see how does this so now we can evaluate this quantity from PC, TC, and VC that we have evaluated here, right? So let us see. So from real gas equation, so what we have done is so we can see R TC by PC VC. So all we are going to do is we are just going to substitute this value. So TC is 8A by 27 RB. So maybe I can do that. R times 8A divided by 27 times BR divided by 9 by A by, this is A by 27B squared times 3B, right? So yes, and yeah, so and you can check that some terms will cancel out. A cancels out here, and B also cancels out here and here, and we are essentially left with, and 27 cancels out, and this is just 8 by 3, and this is basically equal to 2.67, right? So therefore with all these approximations, like the corrections that we have done to the ideal gas equation, from real gas or van der Waals equation of state, we expect the ratio, this ratio to be always equal to 2.67 for all the gases, right? and we can already see that this is not such a bad answer, right? uh, I mean, it's within order of magnitude, it's quite okay, right? Although it's not matching, right? Of course, the first order corrections that we have done, they are not really accurate, but still it does a reasonably good job in at least giving us some sense of of deviations that real gases undergo from ideal gases. All right. Um, Okay, so now what we'll do is, like I said, we'll now do the comparison of Andrews experiment with what we saw from the real gas equation. Okay, and we'll just try to highlight some important points which come out when we compare the experiment with the theory. Okay, so I'm quickly going to draw the Andrews experimental data with the real gas equation. Okay, okay, so this is pressure, this is volume, and as a function of decreasing temperature, we see that there are huge deviations from P, from the mathematical scaling of P, scaling with inverse V, so much so that there is a critical point where the pressure is independent of volume, and later on, no matter how much okay, so later on we see that the volume drastically reduces for the constant temperature, right? And we also saw that this boundary that I've drawn with dashed line basically represents the phase transition, right? So here we have gas, here we have gas plus liquid, and here we have liquid, and this is Andrews experiment. Right. Now we can see what we observed. So now we'll draw the similar behavior or similar relationship between P and V as derived from, or as plotted from van der Waals equation, right? So this is real gas equation, right? So here also we saw that if our temperature is very high, we can ignore the term which contains A, which basically measures the degree of intermolecular attraction, right? So for small a, so P scales inversely with V, but of course when we start introducing the effect of A more and more, this expression will start deviating, and here also we will see a point where P becomes independent of V, but as we keep on increasing the effect of A, the system will develop a minimum, right? Okay, so what I'm saying is, here P goes as 1 by V minus B. This is the critical point, let's just call it X in both cases, and here we see a minimum, right? Now the first thing that stands out when we compare these two curves is that up to point X, the comparison is quite okay, but as we increase the value of A, or by which becomes more okay. So when I say small a, so this is also decreasing T. Okay, so this is increasing A. So along this direction the A is increasing, and maybe I can write here. So the relationship that we are plotting is P equals RT divided by V minus B, and this point obviously will be B minus A by V squared, right? So as we increase the value of A, we start deviating from the Boyle's law, right? And you can imagine that the effect of A will increase at lower temperatures, right? As you decrease the temperature of the system, the kinetic energy goes down, and potential energy starts playing greater and greater role. Okay, so this is along this direction the temperature is indeed decreasing. All right. Okay, so the first thing that stands out is that we do not really see any minimum here, all right? We see a flat line. On the other hand, from real gas equation, we see a very well defined minimum, all right? So what's going on? Okay, so first I would like to draw your attention to the experiments, right? So just see, so imagine when you are in, okay, so what's going on is that when you are in a gas phase, so like we saw, so we basically, if I'm not wrong, so we basically divided this curve into 4 parts, and I think I call this A, I call this point B, I call this point C, and this is D. So between A to B, so P scaled with inverse P, right? Because here CO2 is gas, right? But between B and C, so P independent of volume, and between C to D, uh, uh, P increases sharply. All right. Okay, so let's try to understand this. All right, this is important. So when carbon dioxide is gas, right? So we can expect the Boyle's law to still hold true, right? So at very low temperature, when the volume is still very high, so the gas molecules are not interacting with each other and they behave like an ideal gas. But at certain point, which is B, there undergoes a phase transition, right? So essentially what happens is, so these carbon dioxide molecule which were in gaseous phase, they suddenly undergo a phase transition where some of the carbon dioxide molecules, they phase separate into a liquid phase, and there are very few carbon dioxide molecules in the gas phase, right? So this is basically liquid and this is gas. And at this time, at this point, since many of the gas molecules, they go into liquid phase, they do not exert any pressure on the wall, right? Or even if they exert any pressure, that is very, very low. So therefore, suddenly the pressure, suddenly for a constant pressure, the volume of the system goes down, right? So remember, we are applying some pressure here, right? And since there is a phase transition, many of the molecules, they go into liquid phase and there is no resistance from the gaseous phase, and suddenly the volume drops abruptly, right? So you can see that volume drops from B to C at the constant pressure, right? So at constant pressure, the volume suddenly goes down, right? So much so, so the volume suddenly goes down, and that means, so if you think that this is the piston, suddenly your system, so your piston will get in contact with water, right? So with liquid phase. So you have these carbon dioxide molecules which are now in liquid phase, and your volume, okay, so what I'm saying is, here the volume is VB, here the volume is VC, and you can see that VC is much smaller than VB, okay? But now at this point, what happens is your piston is almost touching the surface of the liquid, right? And liquids have much higher density than gas, right? And it's almost impossible to compress a liquid phase. I mean, it is possible, but you need huge amount of pressure. So therefore, in order to decrease the pressure of this system further, you have to apply much greater amount of pressure, and that explains this sudden divergence of this pressure curve, okay, as a function of decreasing volume. But the important point is that we see a plateau because there is no resistance, right? There are no gas molecules to resist the external pressure, so the volume of the gas decreases abruptly. On the other hand, when we now let's go to the theory, right? So when we formulated this theory, we assumed that the pressure of the gas is still well defined, right? No matter what happens. So therefore, in real case, in this theory, we are assuming that even when the phase transition has happened, the pressure is well defined, right? But that is clearly not true, right? Because there are hardly any molecules in the gas phase. So therefore, the volume decreases abruptly, but because of that assumption that we made, we see a minimum. Okay, so I hope that is clear, and I want you to go home and go back and think about it. All right, so this curve, or this appearance of this minimum, is because of the assumption that we made that pressure is well defined even when we cross the phase transition point. All right, and okay, so I want to say one more thing about it. So you can see that from this point to this point, right? So from this point to this point, so remember, these are at constant, so this curve is at one constant temperature, right? So at this point to this point, our dP by dV is positive. Okay, now I again want you to think about it, right? So no matter what system you have, if you increase the pressure on that system, right, its volume has to go down at constant temperature, right? So for example, if I apply some force, what's going to happen on a container? If I compress the so if I decrease the volume, what that means is the molecules are getting closer and closer to each other, and that has bound to decrease the pressure, right? So okay, so the increase the pressure, right? Because there are more and more molecules, the frequency of molecules hitting the container boundaries, that increases, right? So what I'm saying is that so maybe I can go to next page, and I can draw this again quickly. So this minimum that we saw, so I can, okay, so this is P, this is V, and I'm saying that from this point to this point, dP by dV is positive, right? And my claim is that dP by dV is always less than 0, always, right? Because it is absurd to basically think that if you decrease the volume of the system, the pressure also the pressure will decrease, right? So pressure has to increase. So this has to be a negative quantity for all systems decreasing, V increases, P, or vice versa, right? Or increasing, P decreases, V. Okay, so therefore the sign of this quantity has to be negative. But in this theory, we see that the sign of this quantity is positive. So therefore that is exactly what does not happen in the real system. And in experiments, rather than seeing a minimum, there is a plateau, right? Because at most dP by dV can be 0, right? It can never be greater than 0. Okay, and this basically explains the comparison between the real gas equation, the pressure versus volume curve that we obtained from real gas equation, with the Andrews experiments. Okay, all right, so I hope that point was clear. So now I'll quickly talk about limitations, right? So what we have done so far is we have defined the real gas equation. We have made some sense of we have actually got little success in explaining the experimental observations from this first order correction that we do to the ideal gas equation, but there are still various limitations to this theory, right? So limitations of Van der Waals equation. So one limitation that stands out is that we assumed A and B to be independent of temperature, right? So we assume that these corrections that we called A and B, A for the intermolecular attraction and B for the finite size of the molecule, they both can depend upon temperature, right? So it doesn't have to be constant, and we already see signatures of that, right? You can see that RTC by PCVC is not really constant for all the systems. So it does vary, right? Um, so that is one limitation. It's not very straightforward to include that variation in this theory, variation of these parameters as a function of temperature. Also, the other limitation, which is very clear, is that RTC by PCVC from this theory is 2.67 from theory, from theoretically, whereas experiments showed this to be varying between anywhere between 3 to 3.5, right? It varies between 3 and 3.5. So clearly this mismatch is there, right? So even though it does a reasonably good job, but it doesn't really predict the numbers accurately, right? And the third, the most severe limitation is that it fails beyond critical point. And therefore cannot really predict phase transition, right? Can't explain the physics of phase transitions. Okay, so these are a few limitations. And one last thing that I will do in this topic is basically to talk about what's known as reduced equation of state. Alright, and what is reduced equation of state, right? So remember, remember, since the theoretically predicted values don't match with experiments, and we also believe that these parameters A and B are not really constants over the entire range of temperature, and also they vary greatly between system to system, right? There is no reason for A and B to be same for, say, carbon dioxide and helium, right? So it's sometimes better to express the real gas equation in terms of what's known as reduced variables. All right, so let me define that. So we can eliminate A and B from real gas equation. Okay, and how do we do that? So we can define reduced variables. Okay, so these reduced variables, they are denoted as subscript R. So this is P divided by PC, where PC is the critical pressure. Similarly, we can define reduced pressure as V divided by VC, where VC is the critical volume, and similarly TR is T divided by TC, where TC is the critical temperature. Okay, and what we'll do is we'll substitute these values in the real gas equation, right? So basically substitute in the equation P plus A divided by V squared times V minus B equals RT. Okay, so you just substitute for P equals PRPC, V equals VRVC, T equals TRTC in this equation, which I'll do. So this becomes PRPC plus A divided by VRVC squared times BRBC minus B equals R times TRTC. Okay. And next that we'll do is we'll basically again substitute BC equals 3B like we evaluated before, TC equals 8A divided by 27RB, and PC equals A by 27B squared. Okay, and if we plug these values in this equation, so we basically get so PR times A divided by 27B squared plus A divided by 9B squared BR squared times 3B BR minus B equals, so 8A divided by 27RB times RTR, right? And we can see some quantities they cancel out conveniently, and there is little bit of algebra, so which we can simplify this as follows. So so you can convince yourself that this simply can be written as A times PR by 27 plus 1 by 9 VR squared times 3VR minus 1 equals 8 by 27 times TR. Okay, so I have actually taken some terms out of these parentheses and cancelled some common terms of on left hand side and the right hand side, and this is what we get. And if we simplify it even more, right, so let's take 27 out and cancel it with that, so you can check very easily that eventually what we get is the following equation. So PR plus 3 divided by VR squared times VR minus 1 by 3 equals 8 by 3 TR, right? So this is like the modified or the real gas equation written in terms of these reduced variables, right? And this is also known as reduced equation of state for a real gas. Okay, so that basically brings the end to the topic of kinetic theory of gases, and maybe I will quickly summarize what we have done before we start the new topic of thermodynamics in the next class. Okay, so before we end in the next 5 minutes, I will quickly summarize what we have done so far in the kinetic theory. So summary of kinetic theory of gases. Okay. So basically we started with a very simple system which is basically a collection of molecules which are non-interacting, which are point-like dimensionless molecules, and we saw that these molecules, they always exist in a state of a gas, right? Because the contribution to the total energy is always kinetic energy, right? So basically this is a theory of non-interacting dimensionless molecules which for these reasons are always in gas, right? So gas phase. So this theory is like strictly applied, can be only applied to the phase of matter which we define as gas, right? So that is like one of the limitations. We can't really accurately apply this theory to liquids or solids, okay? But it still gives us a decent way of understanding some interesting thermodynamic variables, right, like temperature and pressure. All right, so later we defined or we evaluated or we basically introduced, we understood the concept of pressure. Okay, like we basically designed the problem in such a way that we have a container in which we have some gas molecules, and gas molecules are not interacting with each other, they are not even colliding with each other, they are directly colliding with the walls, and every time the molecule collides with the wall, it imparts some linear momentum onto the wall and its own velocity changes direction, and there is rate of change of momentum per unit area per unit time, and very easily we can just evaluate the expression for pressure, right? And this can only be done accurately if your gases are not interacting with each other, especially if we ignore the attractive interaction. All right, so we understood the concept of pressure. Later we defined the concept of temperature, right? So we defined the kinetic, so we did kinetic interpretation of temperature. And the way we did was that the temperature is nothing but 2 by 3 times epsilon, where epsilon is half mv squared average. This is the average kinetic energy of one molecule. Okay, so this is how we defined the temperature, right? All right, so the next thing that we did was we also evaluated the molecular the molecular speed distribution, right? So molecular speed distribution, right? And which was as follows. So we defined dnv by dv, where v is the velocity, is given by 4 pi n times m divided by 2 pi kbt raised to the power 3 by 2 times v squared times exponential of minus mv squared by 2 kbt, and this is also known as Maxwellian distribution of molecular speeds. Right? And we saw that how it varies with temperature, right? And this basically tells us how many number of molecules are moving with certain velocity between a given range of dV, right? So basically it gives you the probability of a gas molecule moving with a certain speed. Okay. And later on we introduced the concept. Okay, so later on we started relaxing these assumptions for the kinetic theory. So the first assumption that we relaxed was that the molecules are not dimensionless, they have some finite size, in which case there is probability that they will undergo collisions with each other, right? So we considered finite size of molecules which led to intermolecular collision, right? And from there we defined the concept of mean free path, right? So mean free path, which we defined as the average distance a molecule moves between two successive collisions, right? And we saw that it scales as follows, where n is the number density of these gas molecules and d is the diameter of those gas molecules, right? And using this concept, we also considered the situations where the gas was driven out of equilibrium, right? So basically we did transport properties for a gas driven out of equilibrium. Right? And we basically drove the system out of equilibrium using three things, right? In first case, we said that there is a velocity gradient along a certain axis, right? So velocity gradient, or finite velocity gradient, which is a non-equilibrium case, right? That leads to the concept of viscosity, right? Because there is a momentum transport along that axis, and we defined that as eta, and we saw that from this theory, this predicts that eta should scale with square root of temperature, and that also is more or less matches with the experiment. Okay. Similarly, we in the second case we introduced finite temperature gradient, right? Which means in certain corner of the box the molecules are moving much faster than the other corner, so therefore there will be a net energy flow, which is heat flow, and in this case we defined the concept of thermal conductivity. Which we denoted by symbol K, and that also scaled with t raised to the power half. Okay, and later the third case was the finite density gradient, right? We assumed that there are more molecules in one corner of the room than the other, and in which case we expect a diffusion of these molecules, right? And we defined the concept of coefficient of diffusion, and from this theory we saw that this coefficient of diffusion should scale as t raised to a 3 by 2 and p raised to the power minus 1. All right. And finally, which is point number 7, and finally we did corrections to the ideal gas equation, which we defined as van der Waals equation of state, right? And which is as follows: P plus an squared by v squared times v minus nb equals nRT. All right, where this parameter a, this accounts for intermolecular attractions, and the parameter b accounts for finite molecular size, right? And finally we compared compared this real gas equation with Andrews experiment, right? And we saw that the theory matches reasonably well, at least it qualitatively captures some important features which were observed in Andrews experiments. But again, towards the end we talked about certain limitations of this kinetic theory, that it can only be applied to gases. It can't really explain the physics of phase transitions, and that is what naturally takes us to the new topic, which is known as thermodynamics, and that's what we will start in the next class. All right, thank you.